Okay, good morning. First thing I should remind you about the homework assignment 3, which is a programming assignment. The assignment due is on November 3rd, which is Thursday, okay, Thursday night, 11:59. So if you got any questions, you either should try your best to go to the TA office hours to discuss with TA on a particular problem. Okay? Or you can post something on Piazza. But I saw somebody post a concrete code. You say, I just got a core dump or get something stuck somewhere. Of course, you can ask some help from TA or from your classmates. But you try to really, debug your core dump. In many cases, you really have to spend some effort because, in the future you go anywhere to work, you got a program, right in the middle, you got a core dump. Definitely, other people will be, hardly be able to really help you because it's your code, your reasoning, and your writing. It's very hard for other people to get into it, quickly find out your own bug. Right. So try your best. Program assignment always takes time. Okay. Actually, the next assignment is also a program assignment. Okay. Assignment number 4 is a program assignment, more on the classification side. Okay. The reason we put the programming assignment in the middle is obviously we don't want to labor you at the end. Okay, the very end, you get a program assignment. You got lots of things to do. That's pretty painful. So to learn something right in the middle is not too heavy. Probably you still can handle it nicely. Okay. So that's about the course. Also for midterm, anybody, you still have anything not clear about midterm exam, the answers or what should be the answers. Last time we briefly went over. If you still have questions, you're welcome to come to my office hours, or you go to TA's office hours. Okay. And remind everybody in the final exam, the first half will still be covered, maybe 40% or so. You still need to take care of anything you are not very clear in the midterm. Now we are going to get into the last section about the basic techniques of classification. Okay. If you look at the slides you downloaded earlier, I actually shift some slides, which is a rule-based classification. I shift it down to the advanced part simply because the new rule-based one need to use more advanced concept. So I shift down there, merge with pattern-based classification. So that implies we may even finish this chapter a little earlier than scheduled, so we can go to the next chapters, which is still classification. Okay. Last time we discussed naive Bayesian classification. Okay. Remember we said the classification, we will introduce two most basic classification methods. One is decision tree induction method, which is very straightforward. You can see it. You just form a nice compact tree. Okay. The naive Bayesian classification is basically based on Bayes' classification methodology, but you assume all those variables you got is mutually independent. Okay. Even it may not be really true in practice. If you first do some feature selection, get rid of some features you think they are redundant, then you assume they are mutually independent. You work out the naive Bayesian classification, the model. Overall, it's not too bad. Okay, it's pretty good quality. That's a simple method. Before we introduce more complex methods, okay, we will first discuss about a model evaluation and selection. Simply says, you got classification models. It could be a set of rules, could be a decision tree, could be Bayesian, or many other methods we are going to introduce later. Okay. The problem is how good your model is. That means you got this model, whether you can really trust this model, okay. How much you can trust them. Okay. The model evaluation basically say you need to validate your model. And then you should select a better model, or you know your model is not so trustable, you should be fully aware of it. Okay. That means we want to get a good model. The model is accurate, have good coverage, okay. But we have to know what are the measures we can measure them. Okay. There are many measures we can do. The first philosophy is most people doing this classification, they actually put something into the training, but some other thing they reserve it. Okay. They don't put in the training, they reserve it as validation test set. That means you know those labels. You know what is right or what is wrong. Okay. But you first put something into the training to see the model you derived is good enough to do the classification for the things you already know. You already know the label. Okay. Just thinking about this. Okay. Suppose you go to some medical test center. Okay. The doctor, the experienced doctor, you know, they want to check whether this assistant or this interns, they are really good on judging the disease. Maybe the doctor may put some cases, they know clearly these are the cancer patients, okay, but they don't say it. Okay. Then they put the remaining one into the training. Okay. And the training, they simply says, the doctor, the interns may work out some model, say, oh, this one is cancerous, this one is benign, so they can classify patients. Okay. Then this model, the doctor wants to do the text. Simply says, doctor put a new case. Say whether this one is cancer patient, is cancerous, or is benign. Okay. If the doctor put this to test the intern you can think is a classification model because you already got some experience. Okay. If the intern give you the right answer, say, oh, you know it's cancer patient, it's cancerous, and the intern said, yes, it is. Okay. Or you think it's not cancerous, the patient, the intern will give you the right answer, then you think this intern is trustable. Or you can say this classification model is trustable. Okay. That means you always need some validation test set. Okay. You already hold those labels, you want to test it. Okay. The problem is, how do you test this? There are many, many ways to do this. We're going to introduce a few, including hold out. That means you hold some samples hiding there. Okay, you later you can come back, or you can do cross-validation. That means you partition the data into some portions. You take turns. This is training, the remaining is testing, and you take turns. The other become training. You work out several models to see how these models are good. Okay, or you can use bootstrapping. And we also can compare different classifiers. Now we get into details. That means you really got a classification, you have different training testing. We need to evaluate the model you constructed, like decision trees or non-Bayesian classification models. How good your model is. The testing usually is partitioning into this thing, into a confusion matrix. The confusion matrix actually containing 2 by 2. Okay, it's it's very simple, simplest matrix you can think. Okay, one part is actual class. Simply says, you already know the label, you know the actual. This one is cancerous or not cancerous. Okay, so suppose you got one is class C1, the other is not class C1. Of course, if you have 2 classes, you can say one is C1, one is C2. Okay, so this is yes or no, you can think in that case. And then you have every row actually means predicted class. That means your model will predict whether this particular sample is C1 or not C1. Okay, then simply you can think of the cancer. The case you can say the model will predict this one is cancerous, this one is not. Okay, so that means this 2C1 means different thing. Okay, this is the expert hiding the true label. Okay, this row actually is what you predicted, what your model predicts. Okay, so now we have the check. The check, you can see there are 4 slots. One slot we call true positive, means you predict it's positive. The expert check it, it is really positive. That means you said this one is cancerous. The doctor, the experts look at it, it is really cancerous. That means your prediction is right. Okay, that means true positive. Okay. The other one is false positive. What is false positive? That means the true label is not cancerous. You said it's cancerous. Okay. That means you predict it's class C1. Actually, it's not. Okay. We think you think C1 is like a cancerous is positive. So what you got is false positive, false alarm. That means you said, oh, this one's cancerous. Actually, the doctor checked it. It's not. Okay. So that means you sound false alarm. That's why I get false positive. Okay. Then the third one is you said it's not cancerous. Okay. You said it's not class C1. But actually it is. You got false negative. That means you claim it's negative. Actually it's positive. It's false negative. The last one is true negative. It means you claim it's negative, and the true label is also negative. That's true negative. Okay. Those 4, the measure actually is very different because once later we are going to see, negative and positive sometimes it's a very important thing. Okay. You think about it. If you got cancer, you go down there and say no. Okay. The doctor say no. Okay. Actually, you will not trust this doctor. You will find it very terrible because early diagnosed cancer can save your life. If the doctor say no, you have no problem. Actually, the doctor do more harm than good, right? So that's why sometimes you have to thinking about which one is false is more important, or like this false positive. Sometimes, of course, you get scared, but you do further testing, you rule out you have no cancer. Okay, so of course you get scared, but the consequence is not like a false negative, right? So that's the case we have to thinking about it. Every slot, true or false, sometimes they have different consequences. Let's look at this. We still take a buying computer that is, model testing and the prediction. Okay. So you can see we may have these 4 numbers. These 4 numbers, of course, we already explained what they are. Usually you can sum the total in 2 ends. You're probably thinking about it. We did a chi-square analysis. This is something similar to that. So it is similar. Now we will introduce you the terminology, which actually is very important terminology. You probably see the terminology has several very different terms. Even you look at these, just the true positive, false positive, they are all there. But you will see some that we call accuracy or error rate, the other one sensitivity, specificity. We are going to introduce this. This is a very important concept. Okay. The first thing is a classifier. We want to estimate, or we want to evaluate the classifier accuracy. Accuracy means the prediction whether it's really accurate or not. Okay. The accuracy, of course, you want the best one is nothing false. You get it. False positive 0, false negative 0. Everything you predict is perfect. But that's the ideal case. In most cases, it's impossible. Even you go down to see a doctor checks something, give you a blood test. There's still error. Okay, so you cannot guarantee everything's 100%. But let's look at how we judge it. Very important one is accuracy. Accuracy means anything you said is right, it's right. Okay, that's accurate. It means when you claim it's positive, it's true positive. When you claim negative, it's true negative. That's the best one, right? So then you get all the things you claim as true divided by all the cases. That's your accuracy. Okay, you just think about this. If nothing is false, all these two things, false positive, false negative, 0, your accuracy will be 100%. Because, for all, you add these 4 together. If these two are 0, your true positive plus true negative will take 100%, right? So that accuracy is 100%. But in reality, in many cases, you can hardly get this. Almost no classifier every time you check is 100% accuracy. And then in the reverse, we call this one is error rate. Error rate means 1 minus accuracy. Or you can think in that way is anything you did wrong, it counts. Okay. False positive plus false negative divided by all. That means you have 100 tests, you have 5 things go wrong. Okay. 5 things go wrong means sometimes you get false positive, sometimes you get false negative. Okay. Then you add them together, divide by all. That's your error rate. So, of course, error rate is smaller the better. The accuracy, the higher the better. But it's the highest one is 100%, right? Accuracy. But in most cases, you think you just use these 2 measures, or you just use 1 measure. The accuracy, you will be very satisfied. But actually, in most cases, it's not. Okay. You think about, in many classifications, you may have class imbalance problem. What is imbalance? You think about, I use this cancers or not cancers. You go to medical test, there are most of things imbalance. You think about it, you go down there, for example, some people check HIV positive. Okay. So you think about it, how many people really get HIV positive? It's very, very small number of people. Right? But if a doctor, okay, suppose the doctor knows nothing about medical science, you just sit there, it's a fake doctor. Okay. But the doctor can get a very high accuracy. Why you can get a very high accuracy? A person came, say, do I get a HIV positive? Say, no, not at all. Okay. So you can rule everybody. Okay. Suppose the HIV positive is 0.1%. Okay. 0.1%. Okay. So what is your accuracy? If you rule everybody out, you get 99.9% accuracy. Okay. Because the real true one is only 0.1%. Okay. You randomly sample one and say no. Actually, your accuracy is very high. But you're going to do nothing good. Okay. The fake doctor and the people got HIV positive, got cancer. You cannot justify at all. You just say no. You get very high accuracy, but you're good for nothing, right? So everybody knows that. Why? We need another important measure is sensitivity. That means if they are positive, how many times you can really detect they are positive? That's the true one, right? So actually, if you think about it, most good doctor actually get accuracy even lower than those fake doctors. The fake doctors say, no, you have no problem. Actually, the real doctor said, maybe you have problem. Okay, you do another test. Okay. Actually, the real doctor may diagnose actually a little lower accuracy, but the doctor has much higher sensitivity. Because if it's true positive, if it's real positive, you claim it's positive, you capture this real positive, real problem once, you are the hero, right? You capture it. So that's the reason you need another measure or sensitivity. What is sensitivity? That means how many true positives you can recognize. If they really got cancer, you look at it, you say that's a cancer case. Okay. So that's the case. You are the hero. The hero means the true positive versus the true positive is the positive you claim versus you claim right versus the real, all the possible cases. If you can, suppose you really get, say, 10 people, okay, you got, cancer. Okay. You capture 9, suppose. So your specificity is 9 over 10. It's not too bad. The fake doctor, you claim everybody is healthy, the sensitivity is 0. You can see, because there are 10 patients got a cancer. You claim nobody. Okay, so your specificity is 0, no matter how many people you tested, right? Or you claim. So that means the accuracy alone is not a very good measure, especially in class imbalance problem. Okay, you have to check the sensitivity. It's a very important measure. Okay. Another is specificity. Specificity is just a little reverse. It's you claim negative is true negative. Okay. That means you say, I guarantee this guy has no cancer, and there's no, you can see that's a true negative and the real negative. You claim negative is true versus the real negative, right? So that's, you probably can see, you can think this P I wrote as P prime is a real P, right? That's a claimed P. That's a, you claimed, but this P is the real P in your the real label. Okay. This is a predicted P. This is the real P. Okay. So you can see this TP versus real P and the TN versus real N should be along this line, along these two rows, right? So that's specificity and the sensitivity. Okay. That means you need these two measures instead of just thinking about accuracy. Then there is another very popularly used measure, actually called precision and recall. How many people know precision and recall? Yeah, we got half of the class. If you study information retrieval, this is the most basic measure in information retrieval. Okay. Why? Because you think about this. In Google, you type something. Okay. Of course, Google will search something out. Do you believe that Google search did not miss anything? Actually, the Google may miss something. Okay. But on the other hand, if the Google can give you pretty high, pretty large number of this one, you probably trust Google a lot. The reason is the recall is pretty high because you search some other engine. Okay. Some other engine may only return a small portion of results. Okay, then you think there are many things missing. So then you probably do not like to trust the other engine. Okay. I actually went to Europe quite a few times around year, say 2005 or so. European those researchers most time they just believe Google. There are so many search engines at time that they were competing. But they tried all the time. They said the other engine returned very incomplete results. But if I go to Google, it's almost anything I search, it gives you quite complete results. That means they are not just trust your precision, but they trust your recall as well. You get a high recall. Okay. So that's why precision and recall is a very important concept as well. Okay. What is precision? Precision means you returned a high proportion of the true negatives, which actually are, you can see this is the true positive and false positive, this is the positive things, right? You return the true positive, actually it's pretty high, so that's a precision. Okay. And what is a recall? Recall means actually you will miss something. There are something actually in there, you may not get them, right? So what you got is, you can see, there's a true positive, there's false negative. Okay. But this TP is the true positive you returned as positive. Okay. So that's a recall. if you go back to this confusion matrix, you probably can see, if you got, let's say this, okay, you have true TP plus Fn. You look at this. This is TP, this is Fn. TP plus Fn is the positive, right? So you can see your recall actually is a true positive versus all the possible ones, right? That means all the things containing this entry. For example, you type something very rare, okay, to Google. If the Google says 30,000 entries found, okay, if you know there's some entry not found, okay, that implies, you know, the true positive is Google found this. There's something Google did not find. Okay, then you still have a false negative. Google say no, you actually know there's somewhere containing this entry. So that means you actually, if you, of course, in reality, it's very hard to find the whole key, right, in the real search. Okay. But actually, in information retrieval, they don't. In many cases, they get a precision recall at the top something, like top 100, top 1,000, because they think they cannot find all of them to judge the Google or any search engine, right? But here we assume you know all. The expert knows it all, okay? So you get all the possible things, and this is what a search engine returns. So then you still have the recall. In many cases, if you know some engine, you already know the real answer, you can judge the precision recall. Okay, so that's a precision recall thing. Okay. Then, of course, the best one is precision recall both 100%. Okay. But in reality, no search engine or no retrieval method can give you almost like everything's 100%. But actually, these two precision recall are somewhat in the reverse, you know, or reverse relationship. That means you get very high precision, everything you return is right. Maybe you miss something because you want to make sure everything you return is correct. Okay. But if you say, I want to get high recall, I grab everything, I think it's the answer I return, likely contains some noise. So the precision may not. That means everything you return, something could not be the case. Google, in many cases, even returns something. You check it. Actually, it's not what you search. That means, you know, especially go down to the very low pages. Most people just look at the top 1 or 2 pages. You think the precision recall really high. But you go down to many pages, you find something you did not ask. Actually, Google return. That means Google want to get a high recall, have to suffer a little on the precision. That means something returned may not be 100% unique. Yes. Yeah, actually, these two, I should say, there's some overlap. If you really look at this, which is a good, you know, like observation, because you look at this one, it's a true positive plus false negative. This true positive plus false negative is P. And you have TP versus P, you get that. Okay. So then your recall and sensitivity to some extent is the same. Okay. So that's true. That's a very good question. What I should say is just that people have different terminology in different domains or different camps. Okay. People in information retrieval, they barely use sensitivity, specificity, but they use precision and recall. Okay. Actually, immediately I'm going to introduce this F1, F measure. Okay. Those are the information retrieval people mostly using this measure, and they use these terms. But if you go to the pure machine learning people, classification people, they actually like to use terms sensitivity, specificity, accuracy, and error rate. Okay. So there are, you know, the definition, if you really look at this definition, like TP plus FP, you go down here, TP plus FP, you get P prime. Okay. But P prime is not defined here. To that extent, actually, it's a little new. But TP plus Fn is P. The P is defined here. You probably can see these two actually have the same, just the different terms, but they have the same definition. But conceptually, you probably can understand why the information retrieval people would like to call this one as a recall rather than specificity, right? Because recall simply says, you find those many things, but there's something I know there you did not give me. That's a recall. That means there are some you call negative, actually it's not real negative, false negative. Okay. So that's a reason recall is very popular used in retrieval business. Okay. So the other one they use it in the classification business. It's more like a doctor, those things, right? Doctor diagnose, misdiagnose, you miss anything or something. Here, actually, it's also you miss something, but they do not think you are definitely wrong. You just, your recall, you get everything, that capability probably is a little suffer. Like a Google, maybe you miss 1 or 2 entries. Recall is not 100%, but it's acceptable, right? So that's the case. And then in most information retrieval, measure, they actually combine this precision recall because these two, you get high precision, likely your recall may be a little low. You want to recall really high, you also return something which is not definitely there. So you get a little noise return. Your precision is not very high. So that's then the best is you measure, you get a balance of both. To get a balance of both, people actually introduce a measure called F measure. Essentially, it's F1 measure. It's just for harmonic mean of these two. That means this two, they just try to find things in the middle. It's kind of average, but they don't want to use the typical average, like add them together, divide by 2. Actually, they use the inverse. They use harmonic mean. Okay. So that's why F measure is exactly harmonic mean of precision recall. But most IR people, information retrieval people, actually do not use exactly F1. They change a little. Actually, the original F measure defined this way. Okay. They say, if you think about a harmonic mean, you can grab this on the here, you put the F down to the bottom, okay, to be the denominator. Then you will say there's a parameter alpha, okay, weighted on both P and R. If you take a little, you want to write it nicely, you introduce a beta, then this two actually is identical. Just beta square is 1 minus alpha. Beta square is 1 minus alpha's inverse. Okay, so that's just it. So in that sense, you can write down like this. Okay, this is very popular used measure, and people actually assign different values. They give it different names. Just different authors work out different measures. When beta is 1, essentially you say precision recall is sort of, I treat everybody just the same. Okay, then you get an F1 measure. In many cases, F1 is used very popularly. But there are others, they give different measures, they give different names. And it's also very popular used in information retrieval. If you want to know more, you should take CS410. Okay, this is Professor Dai's course, is information retrieval course. He will introduce you many other different measures. But here we just introduce in a very simple way. It's F1 and F measure. You just try to balance precision and recall. Okay, you get F1. Of course, the general philosophy is F1 close to 100, you get a very high precision, very high recall. Okay. But usually the F1 sometimes could be pretty low, like 20s, 30s, right? Because sometimes you return too many, but your precision is not high. Sometimes you emphasize the precision, but you miss something. Okay? So that's the case. Now we just look at this one. Okay? We still take this. You can calculate all the accuracy, sensitivity, specificity, recall, and precision. You can see this. Okay. So just one student just pointed out, said that this sensitivity and the recall is the same. Okay, the formula-wise is the same. The number is the same. You can see. You got the sensitivity, get a 300 or 30%. The recall is also 30%. That's true. It's a very good observation. You can see they are exactly the same. But other than that, all the others are different. For example, you look at this. Accuracy here, because you can see you predict it's cancer, it is cancer. You predict it's not cancer, it's not cancer. You can see this is imbalanced case. In a sense, most people do not have cancer. Okay. You can see the real case, the no cancer, and they do have cancer. Actually, among these 10,000 people, only 300 got cancer. Right? But because of this imbalanced class, you really need this sensitivity specificity. You can see this. This sensitivity means you actually got a 30% sensitivity means you capture 30% real cancer. Because there's 300, you capture 90. Right? So that's not so good. But your specificity is not that bad. Most cancer, not cancer, do not claim cancer. We still claim something wrong. They still have false positive. Right? So definitely, if you take this case, you do not believe the doctor is a very good doctor because the sensitivity is pretty low. 70% of the cancer cases you miss. So it's not. Then here you can see the precision recall you can get. Precision, you can see you claim this, yes, but sometimes it's not. Right? So you can see this precision is not that high. The recall is also not. Then you get an F measure, essentially harmonic mean, that is around 30. The F measure is not high as well. F1 measure. So that's a real case you can do the testing. Okay. Like you construct a classification model, you want to use those measures to test how good your model is. Right? Now we got into the game is how do you really do the testing? To do the testing, in many cases, there are two very popular methods, one called hold out, the other called cross-validation. What is hold out? The hold out means when you construct a tree or when you do naivation or any classification, the doctor or the judge, they know some cases they do not put all the labor data asked you to do the training. They hold out certain things. The hold out may be, for example, if you get lots of data, you may say, I hold out 30% of it. 1/3 of data I hold out. And 2/3 I ask you to play, you do the model construction. Then I'll check how good your model is. Okay. That means the training set, you may take 2/3. The test set, you may take 1/3. This actually is very luxury. Okay. Very luxury means you do have lots of training data. Then you can afford to get 1/3 reserved for testing. Another way actually is more popular use called random sampling. Random sampling means I do not originally take anything out. I actually random sample from a big thing. Okay, that means every time when I want to test, I random sample. I put something out. Then you can hold out like k times. You calculate the accuracy. Later, I'm going to give a little more on this one. Okay, this actually involves some kind of boosting or thing. But another very popular use one is cross-validation. Cross-validation, people call k-fold cross-validation. The k, in many cases, people like to use 10. Of course, you don't have to use 10. Okay. What is the k, like a 10-fold cross-validation? The 10-fold cross-validation works like this. Suppose you get 100 cases. Okay. You know the labels. You want to put them into, model construction. What you do is you take this 100 sample data sets. Okay. You partition them usually evenly into 10 portions. That means 10 by 10. You take you partition this 100 into 10 portions. Okay. Then every time you only hold one portion as your testing data. You take 9 portions to do the training. But you do not just hold one forever. You hold one to do one, you construct a model. Then you put this one back, you hold another one. Okay. That means suppose you mark this as 1, 2, 3, 4, up to 10 different, portions. The first time you hold number 1 out, then you take all the others to do the training. The next time you put this number 1 back, you hold number 2, you take the remaining one to do the training. That's called cross-validation. How do you do the cross-validation? That means that you got 90 samples, the people doing the model construction. Once you get a model back, you use this this 10 samples to test it, to see how good it is. Okay. That's actually, that means if you think about it, you get K mutually exclusive subsets, okay, approximately equal size, because you make it too biased, it's not good, right? Approximately equal size. Then at ith iteration, you take a D sub I as your test set, all the others as a training set. Okay. Then finally, you can either average them or you can, it depends on who calculated it. In many cases, they try to say, I average this. Okay. Sometimes they actually got a few different classification models, they pick up the better one. Okay. That's the cross-validation. Cross-validation is also good if you have sufficient testing data, sufficient samples, okay, labeled data. But sometimes, especially in medical science, they would think that every tissue, every sample is so precious. It's not easy. It's very expensive to get it. Okay. Suppose you only have, say, 10 or 20 samples. You want to do this. Okay. What they do is they call leave one out. That means, suppose you get 20 samples. Every time they only take one out. They take all the 19 into the training. Okay. Then you do the training, then come back, just test the single one to see how accurate, how good you can test it. But in that case, they do it 20 times because you leave one out every time you take one. You can think your folding, your K folding is so refined. Finally, every time you only hold one. That's leave one out. It's just an extreme case of K folding. Right? K folding, now you take one out, all the K minus one becomes training. You want the training to be as big as possible. And another one called stratified cross-validation. The stratified means you actually, when you do this, for every time you hold, you want the holding to be somewhat fair. Okay. You just think about election. I do not know how many people already voted. Okay, I actually before class I went down there to do early voting because I don't want to line up on the election day. Right? So I actually went down there. Lots of people in the union. Okay. Do the voting, but fortunately I do not have to wait online because there are lots of people filling the poll, but nobody really waiting. I go there, I got my ballot right away. Actually, the stratified cross-validation in election is very, very useful. You think about this, okay? Suppose for this election, you have people different race, different income, different education, or man or woman, they all have very different proportions. Okay. Then your holding should be careful. Okay. For example, if you say this holding is all women, or this holding are all college educated, or this holding are all certain race, that's not good. Okay. Finally, your validation is not accurate. You can easily see, right? In the election. So in that sense, stratified cross-validation means every time when you partition, you should have the right portion represent the whole population. Right? Then your validation will be more accurate or more unbiased. And likely you get a trustable validation. So this stratified cross-validation basically says the holes are stratified. So the class distribution in each hole is approximately the same as the initial data. Is that clear? I think the election is the best example to do the stratified cross-validation. Right? Okay, so now we look at another method called bootstrap. The bootstrap is you have a very small data sets. It's for, like a labor data sets. Okay. Then you don't want to waste it. You don't want to waste any sample. You say sample is so precious. Okay. And what you do is you take sample to do the testing. Okay. But once you do the sample, with replacement, actually said every time the sample is selected, it is equally likely to be selected again. Simply say you take this sample out, you say this one, I hold it. I want to test it. But you will take it back, throw it back to the whole jar. Okay? That means next time, there is a chance this guy to be selected back again. That means next time you sample, there's a, of course, slight chance you may sample the same thing, exactly the same object. So that one, but the chance is 1 over something. Okay, you have, suppose you have T samples, the chance to select you back is 1 over T, right? So that's it. Let's look at it here. We just say D. Okay, suppose a data set sample you get T tuples or T objects. You sampled D times. Okay, you get D objects sampled D times. Every time, you got a chance is 1 over D. So, yes. Okay. That's a good question. Actually, people did a lot of analysis. Of course, the cross-validation is a very popular use method. It's pretty good. You actually can see it's this, right? But when the sample is very small, when you do the K-fold, each fold you hold is very tiny. And you all use other things to do the test, to do the training. The chance actually to do this random one, there's theoretical guarantee on the accuracy, rather than you take the cross-validation. Essentially, there's no such guarantee theoretically. So that's why a lot of theory people, they like this bootstrap method. Okay. The bootstrapping method that you probably can think about this is because you got a replacement, you can return this one in. Next time you will sample it again. In bootstrapping, you will never do that, right? You will never sample this back again. Because once you drop it, you just take turns. There is no chance you will get this one back again to be your testing set. But this one, you do have a chance. You put it back, there is a chance to get it back. Okay. And to get it back, you can see the chance. If you have D samples, you sample D times. The chance to get, actually the chance you perceive, this is very interesting because when the D is big, this word becomes E minus 1, right? E is inverse, 1 over E. Because this is when this D goes to the infinity, we know you get it to 1 over E. So that means every time you get 63.2%, with this one you can easily calculate. The 63.2% of the original data ended in the bootstrapping. Okay. But the remaining data got into the testing set. You get this. And if you repeat this one K times, you will get an overall accuracy using this formula you can calculate. Okay. So there are a lot of theoretical study on these bootstrap. And this method, people call this one is 0.632 bootstrap, because you actually can see this one's these many original data entered in the bootstrap. That's why they call this bootstrap method is 0.632 bootstrap. So, and for this, you actually can see you will be able to calculate the real accuracy using this formula. And they actually, there are lots of theoretical study on this bootstrapping. They say it's derived something pretty good. But of course, this is just different testing methods. Eventually, you have to improve your classifier accuracy, right? So that's why in the next section, we're going to discuss lots of like Bayesian networks, including the most fashionable like deep learning. We just mentioned it. We just give you a general idea. And we have probability graphic models. We have support vector machines. There are many, many newer classification methods. But here I only introduced the most classical one, decision tree and naive Bayes, right? So, but the testing of this is just the same. You all can use those principles to do the testing to see how good your classification model is, right? Okay, there are a few slides I skipped. If you go down there, you still can see it. But in my lecture, I just skipped it intentionally because the other one is essentially just a t-test, test the error range or something. That's exactly the same as what you learned in t-test in statistics course. I don't want to repeat it. I know, you did not take a statistics course on this. You probably find my slides a little confusing because you need that portion. But people already learned it. You'll find it's redundant, right? So just skip that part. You know there's a very popular t-test to test your range. Okay. But one thing I really want to introduce is this ROC curves. So I will introduce you here. The ROC curves actually, some people call area under this, they call AUC, the area under curve. Okay. The area under curve, under what curve? Under this ROC curve. Okay. Actually, this ROC curve originally, when they started, they called this one as the receiver operating characteristics. This one was actually first used in the Second World War when the radar, because people want to detect the accuracy, the signal you receive. They do signal analysis. They introduce this ROC curve. Then you just take this as a term instead of thinking the real meaning like receiver operating characteristic. Doesn't make too much sense. Because that time you get a radar, you get a receiver. That's the Second World War. The receiver was the most advanced technology, right? Then nowadays, you say nobody wants to use receiver anymore. You use iPhone, right? But anyway, this ROC curves, the interesting thing is to measure this is from the signal detection theory, they derive this ROC curve. Essentially, it's a trade-off between true positive and a false positive rate. Okay. If you think about it, if you're true positive and a false positive rate, you get, suppose every time you test, you get a half and half. Okay. That means you get something is almost like suppose you get even half is true, half is false, but you throw a dice. Okay, you do not know anything about classification. You throw the dice. You say yes or no. You actually get a half true positive, likely. Okay, you get a half true positive, half true negative. Okay, so that means you throw a dice if it's evenly distributed. Your ROC curve is right in the middle because you get a half positive, half negative. You get nothing good. Okay, that means if you random guess, you get this number, this line. Okay, then if your classification model is somehow better than random guess, it should be, right? If somehow better than random guess, that means your curve here should have, you can see, if you get the worst case is you get everything, you finally reach, the true positive. That means everything you included, you finally get 100% true positive. But if you do something better than random guess, you get a little higher than this 45% line. And if your classifier even better in the very small false positive, you also get a very high true positive. Then your ROC curve line will jump very high, then finally reach 100%. Right? So to that extent, people are actually thinking this ROC curve is a very visible, very vivid description of your quality of your classifier. That simply says, if your classifier is better, your curve will cover more things. So the area under curve, the random guess is 50%. 50% because you draw a random line, you cover 50% of the area. Anything better than random guess should be higher than 50% coverage. The best, of course, is 100%, but in most cases, it's hard to reach. But something closer to 1 means your classifier is really good. So that's why people use area under curve as a good measure. Actually, in many cases, people do not even say ROC curve, they say AUC. What is the AUC? AUC means area under curve, under this ROC curve. Okay. So the best AUC should be 1, but in most cases, you can hardly reach this. So you get a 0.9 or 0.8, you think your AUC is pretty good. Okay. People competing on the classifier quality, they look at it, they compare on the AUC. So that's why this one is very, very popular used. Okay. So we just introduced it. This is another very good way to measure it. Yes? Yeah, true positive rate is this. You actually can see we just introduced this true positive, true negative things. You can see this one is true positive, right? And you have the false positive, false negative. You actually can see here. And here is false positive. Here is true positive. This rate, false positive, will finally get a 100%, and the true positive rate get a 100%. If you got it, everything is perfect, your true positive rate, you get no false positive, you get true positive reaching this. This is the best case. Then your curve will be strictly like this. But that's, in most classifiers, you can hardly reach it in reality. Okay. That means that's why people draw this curve to see how much area you can cover comparing to other classifiers. You cover more, that means your AUC is higher, your classifier is better. We can discuss further afterwards if you still have more questions. Now, we look at, nowadays there are so many classifiers or so many methodologies to work at classifiers. So it becomes a big game in the whole classification family. Okay. Then how to judge your model is good? Which model, which classification methods you want to choose, which finer model you want to pick? Okay. There are several things. One, of course, is your classification quality. Quality, we can say classification accuracy, or you can say the AUC curve or something, right? It simply says, my classifier quality is very good. It should be positive, I say it's positive. It should be negative, I say it's negative. That's the best case. Okay, that's accurate. The second one is speed. Speed means some classifiers, they are good, but take a very long time to get it. Okay. I visited Google in March. Actually, my previous student, Ming Ji, told me, said they have two major groups related to the classification or machine learning. One actually is more on the deep learning part in Google. Okay. They can work out the model, sometimes take days. I mean, because of Google, the data is really huge. Okay. And they have lots of machines. They have Perl machines, they have Hadoop, they have all the cloud, the very powerful thing. But even that, to work on the model may take days. Okay. You think about anybody click a button, you say take a day to back, nobody will do it, right? So then they have another very smart one. Okay. They also do this model to do prediction. Okay. For example, which ads you should put it down on this page. That's what she did. Okay. Put the ads on there. And the time required is 0.1 second or lower. It's a sub-second. Okay. So one is days, one is sub-second. They're all doing model construction. You probably can see. But they're both useful because you need to crunching the huge data to construct to get something. Okay. Something will help them to do things in sub-second. You probably can see. That means the speed is still an issue. You know Google, you click a button, the speed is there. You do need the speed very fast. There are so many they call stream data mining. Stream means the data coming, you have to make a decision right away. Otherwise, data are already gone. Okay, those coming and gone also like sub-second or even faster because the data flow is so fast, you have to make the right decision. So the speed is important. That means the classification not just on accuracy. Accuracy is very important, but sometimes speed is very important. The training time, the decision time also. Okay. And robustness is also good because you got lots of missing data, lots of noise data mixed up, whether you still can do high quality job. The robustness. Scalability. Scalability means you may handle your training data in so huge, like a Google scale. You have to dig through the big data. The scalability is very important. Another one is interpretability. You think about doctor. You think about medical doctor. If you work out a model, you give the medical doctor, say you use it to diagnose cancer or something. It's really high accuracy. The doctor actually may first ask you what method you are using, whether you can explain anything. Because the doctor has lots of experience. They watch the patient, they look at the tissue. They actually have a very good intuition whether this one suspicious is right or wrong. But suppose they give you a model, suppose this one is a support vector machine. They work out a very complicated formula, they finally get this. They just say, trust me, my accuracy is 90% or 95%. How the doctor will trust you if you get 95%? Right? So, because you still miss some case. And you need to interpret. You need to say how you get this. That's why a lot of medical doctors say, I need explanation of your model. If you just give me a black box, you say, trust me, this is 99% is right, this one is cancerous. The doctor still need the explanation. Doctor may not believe you, right? So that's explanation actually is not just for doctors, for many experts. That's why actually this year, the KDD conference, the best presentation paper was by Gershwin, somebody, a professor in University of Washington. And his topic is explanatory classification model. I mean, you give me a model, I actually can turn it into explanation. Okay. So that's pretty magic. And he got an award. Okay. That's interpretability. There are many other measures. For example, whether your rules or the size of the tree or size of the rule, those things are also part of the. Sometimes the simpler is better. Okay, you get the same accuracy. Now, we get into another interesting thing is how do you improve accuracy if you have many different ways to do classification. The first important thing people work out are ensemble. What is ensemble? And I probably can give you a simple example. Suppose you have a friend got some serious problem, so maybe cancer or some problem. Okay. The friend said, I go to a doctor. The doctor said, I got this problem. Okay. I'm worried, but I'm not quite sure I got this problem. You think this this patient or this your friend what he or she will do. Most cases, he or she will say, I probably will see another doctor. I may get 3 or 4 doctors. If everybody said I got cancer, I admit that I got cancer, I go to treatment. If only this doctor said I got cancer, I probably were not going through the treatment because treatment is painful, right? Or it hurt me as well, right? So that's a typical way. You do judgment using ensemble. Ensemble means you actually ask more experts instead of just rely on one. The same thing for classification. For classification, you use one method, you work out a model. You may use the same method or a different method, you work out another model. Okay. So ensemble's general idea is you got K models. Okay. Then you ask these K models to do something collectively. For example, vote. Okay. Then you may trust the voting results rather than any particular doctor. That's the philosophy. We call this one is ensemble methods. Actually, the ensemble method, there are 3 popular ensemble philosophies. One called backing, one called boosting, one called ensemble. What is backing? Backing means you actually work out, usually you may use, just thinking about it, even for, we just talk about it, K-fold validation. Okay. K-fold validation, sometimes you got this K-fold, how they use it to make judgment is you got a K-fold, they think the voting of this K-fold, they will trust. But just thinking about this. Suppose you partition this one into 10, okay, different things. Then you do the testing to see whether this is, you construct a model. Then you actually can vote to say what is the best. You finally pick up the highest vote. That actually is sort of backing as well. Okay. Boosting actually is you got this classifier. You may actually use this one going back to train again. For example, this one said it's wrong. You may have some way to put it back and say, oh, I know this one is wrong. I may modify my model, so this is boosting. Ensemble basically is you got many different classifiers. For example, you may use one using decision tree, the other one using naive Bayes, the third one using support vector machine or something. Use a different kind of classifier, but finally you still take the vote. That one for ensemble. So let's look at each one. The first one is backing. Backing, I already said it, you want based on multiple doctors' majority vote to decide whether you really got a cancer or not. So that's a case is similar to this backing idea. The backing idea is suppose you get a D tuples in the set. Okay. Then every iteration you train this using this D tuples or D object to train, you get a model. Okay. You can use different training methods to get a model. For example, we just telling you can use K-fold validation, you get a bootstrapping, whatever you get this. Okay. Then you can get a one model, M1. Suppose you get a training set D sub I, you get M1. Okay. Then the backing basically say you may get M classifiers. Okay. Then you take this M classifier, every time you want to do testing, you take this M classifier to get a different opinion. Okay. You're just thinking about this is one patient. Okay. There are K doctors. K doctor, they take this patient. Every doctor you can think is a classifier because he or she has a particular capability to judge whether this patient is cancer. I mean, this tissue is cancerous or not. Okay. That means each one is a classifier. Finally, you take a bag of classifier. How do you do it? You vote. Okay. That means you take those one, you vote, you count the votes, You sign the majority, the most votes. Okay. That probably is similar to the election. You can think of everybody as a classifier. Okay. So you want to classify those candidates. You want to say yes or no. Okay. Of course, in the general election, you are not taking everybody to count the votes, but at least you can count every state. Right? You say the state who wins the whole state. You can think who wins Illinois or wins Indiana, right? So those are the things you can think of this classifier. Actually, is multiple thing you get back in. Okay, you can say who is the winner. Okay. So that's a backed classifier. Okay. It can be used for continuous value. You can take average, for example. You get a regression. You can take the average of the regression. That's to do the prediction. And people actually tried this way and found it is better than a single class. Because the single one, you make a mistake, you get a multiple one. You can easily justify this by doing some reasoning. Okay, I can give you a very simple reasoning. I can justify this. You can think about this. Suppose you get a pretty poor doctor. It's not a very good doctor. Okay. Suppose in your area every doctor is so poor. Okay, but suppose every doctor, even they are poor, they got a better than half accuracy, then better than random guess. You can think in this way. Better than halfway, you can make it right. Okay. That means the accuracy is just slightly higher than 50%. The error rate is slightly lower than 50%. Okay, suppose you get this. Okay. Then if you have K doctor, you finally to take a vote. What's the chance to really get wrong? You actually can calculate this. If everybody, the error rate, because accumulated error, you can say this is wrong. This guy did it wrong. This guy did it wrong. This guy did it wrong. Finally, because I take the vote, I take the majority. If everybody got wrong, of course, the majority got wrong. You actually can easily calculate the probability. Even just slightly over 50%, you take the majority. The chance you make it right is substantially higher. You can calculate this. Maybe I should put this in the finer exam. You will see what is the rate you will get if you take this back in. Then you probably can calculate the accuracy. The accuracy is substantially, you will see, is lower. Even everybody just get a little over than half. The accuracy is substantially lower now, right? So this is the bagging. You can prove it. People actually prove it, and the people also use it. Even you do not learn this, when you get a problem, it's concern more than one topic. That's actually the bagging already. Okay. Then what is boosting? Boosting actually saying, I can repeatedly do this, okay? And I can take a vote. You can think about, suppose you're also consulting doctors. But you do not take doctor, everybody is equal. You may say, this doctor actually is an intern, just graduated, very little experience. This doctor is very famous. Actually, you get a so big name. Okay. So if you say, I actually can somehow get weights, I can put weights on the doctor, then finally my judgment probably will be far better. You have such case? You do. No. For example, if you got a problem wrong, you say, I asked my friends. But this friend actually is an A+ guy. This friend is a C student. Okay. So which one you trust more? You probably say, oh, this guy is always get A+. I ask, he give me an answer. Okay, this guy get a D, he give me an answer. I could put different weights, right? Even I want them to vote. I trust somebody better than the others. I know how to sign a weight. I will be the winner. Okay. Actually, there was a paper. You probably think it's a joke. Say, how to grade your class without knowing the answer. Okay. So actually, they did the test. They finally found the accuracy is so high. You really can get an automated grader. Without knowing the answer, you just take the whole class and automatically finding out the right answer, give everybody the right score. Okay. So there's some research paper doing this. essentially, you think about it, this is very similar to this back-end boosting. Okay. So we are going to discuss this more in the next lecture. Okay, thank you.